The complex directionally dependent appearance and spatial texture of realistic materials can be captured with modern acquisition techniques. However, making edits to these datasets, such as the one shown here, remains challenging due to their complex structure, large size, and the variety of representations used in practice. We propose a system for editing complex measured materials. A designer first indicates an edit by painting directly onto the surface of a model. For each set of paint strokes, the user specifies the parameters of an edit they wish to apply to the material at those regions. Our system automatically propagates these sparse editing constraints to the entire dataset in a way that respects the complex structure of the data. Because our system returns editing previews at interactive rates, the user is free to add more constraints and refine the parameters of each edit until the design goal is met. Consider this set of strokes a user has applied to the Dove dataset. Recall that they also specify editing parameters that indicate how they want a material's appearance to change below each set of strokes. The goal of our algorithm is to automatically propagate these sparse editing constraints to the unspecified regions in the input, visualized here as blue pixels, in a way that respects the structure in the data and provides interactive feedback so the designer can iteratively refine these constraints. In order to respect material boundaries during propagation, we enforce the policy that points with similar appearance will receive similar edits. This is done by encoding the relationship between all pairs of points by building a sparse graph that connects each point to its n nearest neighbors in appearance. To smoothly propagate edits, we define an optimization problem over the appearance graph. Specifically, the value of editing parameters at each location are chosen to minimize an objective function with two terms. The first term penalizes a solution that deviates from the editing constraints. The second term penalizes gradients in our solution between adjacent nodes in the appearance graph. This has the effect of enforcing the policy that similar edits are applied to regions with similar appearance. As shown here, this optimization has the effect of propagating the user's editing constraints in a way that respects the complex structure in the measured data. We can find a solution to the above optimization by computing smooth regions of influence for each set of strokes. The sparse nature of our appearance graph permits the use of fast conjugate gradient solvers that can return editing previews at interactive rates. Furthermore, once the influence regions have been computed, users can adjust their editing parameters without the need of solving the optimization problem again. In this example, we show an edit being made to a reflectance dataset of polished maple where the user is adjusting the color of the darker grain. Note again that these edits are automatically propagated to other disconnected areas with similar appearance due to the global structure of our appearance graph. We support local edits by adding the spatial coordinates of each point to the distance metric we use to build the appearance graph. The user can adjust a single parameter that determines how much weight is given to these coordinates, thus controlling the spatial locality of adjacent nodes in the appearance graph. Performing the same optimization as before on this modified appearance graph has the effect of restricting edits to influence only a local region. To conclude, we have developed a new algorithm and prototype system that allows making interactive edits to complex measured materials. One key benefit of our system is its independence from the underlying BRDF model. This final editing session shows a user adjusting a time-varying dataset of steel rusting. With just a few strokes, the user specifies an editing constraint to the untarnished steel that sharpens its specular highlight and changes its color. Our framework then automatically propagates this edit to the entire dataset. Because this edit respects its complex spatiotemporal structure, we maintain the realism provided by the measured appearance data.